In this video, we're going to take a look at orthogonal diagonalization. First, let's recall a fact about orthogonal matrices. So if Q is an orthogonal matrix, then Q inverse equals Q transpose. That fact makes orthogonal matrices particularly nice to work with. So with that in mind, let's look at a definition. We'll say that a square matrix A is orthogonally diagonalizable if there exists an orthogonal matrix Q and a diagonal matrix D, so that Q transpose AQ equals D. Now, if you like, you could compare this to the diagonalization formula that we saw in chapter 4. So we said that a matrix A is diagonalizable if P inverse AP equals D, where D is a diagonal matrix. And if you change this interstatement about orthogonal matrices, you'd likely call your matrix Q instead of P. So you'd write Q inverse AQ equals D, except we know for orthogonal matrices, Q inverse can be more easily thought of as Q transpose. So that's where that formula Q transpose AQ equals D comes from. So now let's look at a fact called the spectral theorem. The statement says, let A be a square matrix. A is orthogonally diagonalizable if and only if A is symmetric. Let's remember back when we were talking about matrix properties, we said that A is symmetric means A transpose equals A. So the matrix looks the same when you turn the rows into columns. So spectral theorem gives us a really quick way of deciding whether we can orthogonally diagonalize a matrix or not. If it's symmetric, we can. If it's not symmetric, we can't. So to emphasize this, let's do a quick example. If someone gives us this matrix here, we'd look at that and we'd say, yep, that's symmetric, therefore it's orthogonally diagonalizable. Whereas this matrix here, not quite symmetric. So therefore the matrix is not orthogonally diagonalizable. So here we have a symmetric matrix A. We know it's going to be orthogonally diagonalizable by the spectral theorem, and we're told what the eigenvalues of the matrix are. They're 4 and 7. So our goal is to find the matrix Q that orthogonally diagonalizes A. So we are going to find an orthonormal basis for each eigenspace. The idea is that once we have this basis for each eigenspace, we're going to put these together into the columns of matrix Q. And remember, Q is an orthogonal matrix, so it's going to have orthonormal columns. That's why we need an orthonormal basis for each eigenspace. So let's start with the eigenspace E7 associated with lambda equals 7. So to find our eigenvalues, we're going to solve the system A minus 7i. That's a homogeneous system. So we're just going to go through and subtract 7 from the diagonal entries of A. Therefore, we're going to have -2 all along the diagonal, and the other entries will all stay the same. So we're going to get this matrix here into our REF. So if you want some more practice with row operations, you can check that our REF comes out looking like this. And from here, we'll just focus on solving the system. So let's call our variables x1, x2, x3. If we go through the rows and circle the first non-zero entry in each row, we end up with a couple circles. x3 does not have a circle in its column, so that's going to get a parameter. And then top row says x1 minus x3 equals 0. So if we solve that for x1, that says x1 equals x3, but x3 is t. And similar for the middle row, x2 minus x3 equals 0. So if we solve for x2, that says x2 equals x3, and again, x3 is t. So what we're getting is all our variables equal to t. If we write that up in vector form, we're saying our solution is 1, 1, 1 times t. So what we're looking for is an orthonormal basis for this eigenspace. Since there's just a single parameter here, that vector 1, 1, 1 is going to be our basis vector. And to make that normalize, we're just going to divide by its length. So we would have 1 over root 3 times 1, 1, 1. That is our orthonormal basis for E7. So I've just recopied the matrix A so we can see it, and now we're going to work on the eigenspace E4. So to find our eigenvectors, we're going to solve a certain homogeneous system, and that's going to look like A minus 4i. So let's subtract 4 from the diagonal entries. We'll just get 1s along the main diagonal. So we've actually got a matrix entirely of 1s here, and we've got a homogeneous system. So if we put this into our REF, what we'll find is just a single non-zero row, like that, and then a couple rows of zeros. So there we have our REF, and then from there we can think about solving for our eigenvectors. So going through the rows and circling the first non-zero entry, we've just got a single circle, and that tells us that we're going to have a couple different parameters in this system. So if we call our variables x1, x2, x3, we're saying x2 equals s, let's say, x3 equals t, and then top row says x1 plus x2 plus x3 equals 0. So if we solve this for x1 and just use the values of our parameters, x1 is minus s minus t. Okay, so then from there we can write up the vector form of our eigenvectors. So we're going to have some numbers times s plus some numbers times t, and our coefficients are going to look like -1, -1. x2 is s, so that's 1 times s and nothing times t, and x3 is t, so that's nothing times s and 1 times t. All right, so if we wanted to write down a basis for this eigenspace E4, we would just grab these two vectors, -1, 1, 0, and -1, 0, 1. But we actually want to take this further because what we're looking for is an orthonormal basis. So that means we're going to do the Gram-Schmidt procedure. So we'll get a little bit more practice here with our Gram-Schmidt procedure. We're going to turn this basis into an orthogonal basis, and then we will normalize at the end. So if you want, you can just convince yourself right now that these two vectors are not orthogonal. When you take the dot product, you don't get 0. And that's what tells you you need to do Gram-Schmidt in order to orthogonalize this set. So we should be able to do that part pretty quickly. Our first vector requires no algebra. We just take that first vector and we put that into our partial basis, which we can call x if we want a short name for it. So after step 1, you've just got a single basis vector. And then things get interesting when we start to build our second basis vector. So we're going to take the second vector from our set, which was this -1, 0, 1, and we need to subtract off its projection onto x. So projecting onto our partial basis, what we're projecting is this vector -1, 0, 1 that we're working with. So what this does is this gives us something that's now perfectly perpendicular to our partial basis x. All right, so let's run through the algebra. We would have -1, 0, 1 minus. To do our projection, we're going to be doing the dot product of this vector here with our vector in x. So just highlight the two vectors we're going to be working with so we can see them. So dot product is 1, and then everything else is about the vector that you're projecting onto, which is this guy here. So length squared is 2, and that vector is in the direction -1, 1, 0. So remember with Gram-Schmidt, you're free to scale vectors to avoid fractions. So it might be easier here to work with 2v2. That would give us -2, 0, 2. And then we'd just be subtracting off a full multiple of -1, 1, 0. Okay, so I think just to save space, I'll write the result here. So -2 plus 1 is going to give us -1. We're getting another -1 and then a 2. So at this point, we have our orthogonal basis. So the -1, 1, 0 that we had from our first vector, and we've now built a vector that's orthogonal to that -1, -1, 2. So you can just do a double check here, confirming that these two vectors are orthogonal. they are. They have dot product 0. So that tells us that we've done our algebra correctly. So remember, what we were looking for was an orthonormal basis for each eigenspace. So we're now about to write down an orthonormal basis for the eigenspace E4. And all we need to do here is just normalize these two vectors so that they've got length 1. So the first vector has length root 2, therefore we should write 1 over root 2 times that vector. And second vector has length root 6. So we'll write 1 over root 6 times that second vector. And there we have an orthonormal basis for E4. Remember that earlier in the problem, we found an orthonormal basis for E7. So I'll just write that down again so that we've got all the ingredients in one place. So it was 1 over root 3 times the vector 1, 1, 1. So remember, the question was asking just to find the matrix Q that orthogonally diagonalizes our given matrix. So what we're going to do is just put these basis vectors into the columns of Q. You can put them in any order that you like, so I'll just put them in the order that we found them in. So this first vector here, we need to divide each of the components by root 3. So we need to write things like 1 over root 3, 1 over root 3. Now let's do our second basis vector. So we're looking over here at E4. So we'll write minus 1 over root 2, 1 over root 2, and 0. And then on to our third basis vector, minus 1 over root 6, minus 1 over root 6, and 2 over root 6. And there we have our matrix Q that orthogonally diagonalizes A. So a couple of comments about this now that we're done the problem. First thing is, if you wanted to check your work, you could confirm that Q transpose AQ does come out to a diagonal matrix. And what we should see along the diagonal are the eigenvalues of A in the order corresponding to the order of the columns of Q. So our first column corresponded to the eigenvalue 7. So we should see a 7 in the first position. And then the next two were coming from the eigenvalue 4. So we should see 7, 4, 4 in that order along the diagonal and zeros everywhere else. Second comment, when A is a symmetric matrix, the eigenvectors for different eigenvalues are orthogonal. So let's take a look up at our matrix here. See, this first eigenvector here corresponded to lambda equals 7. And then these other two corresponded to lambda equal 4. So what we're saying is that if you grab two eigenvectors associated with different eigenvalues, they will always be orthogonal. That will be true anytime you start with a symmetric matrix. So these two highlighted vectors here are orthogonal, and similarly these two eigenvectors here are orthogonal. So when you're thinking about applying Gram-Schmidt, that's actually good news, because that means you only ever need to do Gram-Schmidt on one eigenspace at a time. We had to make sure these two highlighted vectors were orthogonal to one another, but guaranteed they would be orthogonal to eigenvectors associated with any other eigenvalue. So before we can get on to our second big idea of this video, we're going to recall something called the outer product expansion, which we saw in section 3.1. It was just a very specific way of multiplying matrices that we're going to use in the second part of this video. So let's think about normal matrix multiplication. Normally we're programmed to think about circling the rows of the first matrix and the columns of the second matrix and doing our dot product. So that's the normal way of doing things. The outer product expansion tells us to circle the columns of the first matrix and the rows of the second matrix. And it says an alternative way of multiplying these two matrices is actually just to take the first column and multiply it with the first row, and then go plus the second column times the second row. So if you're multiplying two 2 by 2 matrices, you'll just have two terms in this sum. If you were multiplying 3 by 3 matrices, you'd have 3 terms in this sum. Okay, so let's multiply this out and let's confirm that this really does give us the correct product. So when we look at this is a 2 by 1 matrix times a 1 by 2 matrix. So what we're going to be producing is actually a 2 by 2 matrix. If we take the first row, it's just got a single number in it. So this is just saying multiply this number with the first row and you get 5, 6. Now multiply this number 3 with this row and you get 15, 18. So we're just doing products of numbers. There's no dot products involved at this point, just multiplying numbers by other numbers. And then we're going to add this to, again, we're going to have a 2 by 2 matrix. So take the number 2, multiply it through that row, you get 14, 16, and then take the number 4, multiply it through that row, you get 28 and 32. Okay, so now it's just a matter of adding these two matrices together. So we get 19, 22, 43, and 50. So let's just confirm that this works. And the way we would confirm is we would take our matrices, so 1, 2, 3, 4, 5, 6, 7, 8, and let's just do the normal matrix multiplication. So we would circle the rows of the first matrix, columns of the second matrix, and now we're doing dot products. So yep, we would get 19 and 22, that's looking good. And then with the bottom row, we would get 43 and then 50. So yes, in fact, the product of these two matrices is 19, 22, 43, 50. And we were able to arrive at that through this other process called the outer product expansion. So we'll see this idea of outer product expansion is exactly what we need to have the second part of our discussion. Now let's look at an important definition. Suppose that you have a symmetric matrix A, and let's say that you have orthonormal eigenvectors for this matrix. So to emphasize that they're orthonormal, we'll call them Q1, Q2, Qn. And those are corresponding to some known eigenvalues, lambda 1, lambda 2 through lambda n. So given that, we can build what's called the spectral decomposition of our matrix A. And what that does, it describes A in terms of its eigenvalues and eigenvectors. So the formula is take the first eigenvalue, multiply it by the first eigenvector, and then multiply that by itself transposed. And you're just doing a sum of things like that. Q1 is going to be a column, and Q1 transpose is going to be a row. So we're going to be multiplying a column times a row, and this is why we discussed the outer product expansion, because that's just going to help us with the actual algebra of multiplying this thing out. So we're going to find a 3 by 3 matrix A with eigenvalues 2 and 3, and we know something about the eigenspaces. Let's go back to our spectral decomposition statement and just figure out what's required. So what we need are is a set of orthonormal eigenvectors. That's what's important here. So that's why we're calling those vectors Q1, Q2, just to emphasize that it's an orthonormal set. So we'll say vector Q1 is 1 over root 3 times 1, 1, 1. Eigenvector Q2, 1 over root 2 times 1, negative 1, 0. And we'll say eigenvector Q3 is 1 over root 6 times 1, 1, negative 2. So this is an orthonormal set of eigenvectors. Now with that, we can write down our spectral decomposition. So what that does is builds a matrix A that has the specific eigenvalues and eigenvectors. So the formula is to go lambda 1 times Q1 transpose, plus we're going to have two other terms for the other eigenvectors. So a couple of comments about this. It is important that we're writing our eigenvectors in column form so that when we multiply this out, we're multiplying a column times a row. And the other comment is that you might just want to have your eigenvalues written down somewhere near the eigenvectors so that when we're doing our calculation, it's a little bit easier. So the first two corresponded to eigenvalue 2, and the third one corresponded to eigenvalue 3. Okay, so that way we can have all the information on the screen at one time. So let's plug in and find our matrix A. So we're going to take our first eigenvalue times our first eigenvector. So it's going to be 1 over root 3 times 1, 1, 1. And then we're multiplying by the transpose of that. Okay, so there's going to be another factor of 1 over root 3, which I'm going to write in front. Put all your factors out in front. And then the transpose vector looks like 1, 1, 1. So we're going to do that for each of these terms. So we'll have 2 times a 1 over root 2 times another 1 over root 2. We'll have our vector and then the transpose of that. So 1, negative 1, 0, and then that transposed. Okay, and then we'll go plus, I'm going to write the third term on the next line. Our eigenvalue is 3, and our eigenvector had a 1 over root 6. So we're going to get a 1 over root 6 times our column times our row. And our vector looked like 1, 1, negative 2. So now it's just a matter of getting this multiplied out, and then we'll have our matrix A. All right, so let's collect all our coefficients together. So we would have 2/3. And then when we multiply this vector times that vector, we're thinking outer product expansion. So we're going to have a 3 by 3 matrix. Let's multiply the 1 times that entire row, 1, 1, 1. Then multiply this one through your vector, 1, 1, 1. And then multiply this one through your vector, 1, 1, 1. So that first term was particularly easy. I think it'll get more interesting as we go. So for the second term, we've got 2 over root 2 over root 2. So that's 1. And then we'll do our outer product expansion. So first number times that row, 1, negative 1, 0. Second number times that row, negative 1, 1, 0. And then multiply the 0 by that row, you get a row of zeros. Okay, so we're making progress here. And then third term, 3 times 1 over root 6 times 1 over root 6. Let's call that a half. And we'll do our outer product expansion. So the 1 multiplies with the row, then the 1 multiplies with the row, and then the negative 2 multiplies with that row to give negative 2, positive 4. All right, so we're going to put this all together into a single matrix. What we may want to do now is just create a common denominator for the coefficients. So let's put all the coefficients over 6. We would say that's 4 over 6 for the first coefficient, 6 over 6 for the second one, and 3 over 6. So I'll show you a fast and slow way of doing the algebra. I guess I'll do the more systematic way first. So notice everything's over 6. So for sure we're going to have a big 1 over 6 out in front here. If you wanted to take your time with the algebra, you could multiply each numerator through. So multiply the 4 through, you'd have things like 4, 4, 4. Multiply the 6 through the second matrix, you'd have things like 6, negative 6, 0. Etc. And then multiply the 3 through your third matrix. So things like 3, 3, negative 6, etc. And then you've got your 1 over 6 out in front. That applies to all 3 of these matrices. So that way you could then do the addition here and then come up with your answer. Now, a faster way of doing this is just to recognize everything's going to be over 6. So we'll keep a big 1 over 6 out in front. And then if you want your upper left entry, you'd go, well, 4 times 1 plus 6 times 1 plus 3 times 1. So that's 13. And then if you want, say, row 1, column 2, you'd be going 4 times 1 plus 6 times minus 1 plus 3 times 1. So if you had a calculator, you could just be typing that in probably relatively quickly. So that would be 1. And we'll just do the same thing all the way through the matrix. So for the top right, it's going to be 4 plus 0 minus 6 is negative 2. So middle row is going to come out to 1, 13. And then for this position here, we've got a 4 plus a 0 minus a 6 is going to be a negative 2. Okay, and then bottom row we get minus 2, and then in our bottom right we've got a 4 plus a 0 plus a 12, so 16. So there we go, we've found a matrix that has the given eigenvalues and eigenvectors. So that's really useful if you're trying to model a real-world problem and you've made some physical observations and you have a sense physically of what your eigenvalues and eigenvectors look like, and you now want to encode a matrix that represents that system. That's essentially what we just did. If you wanted to check your work here, sometimes nice to do the first time you solve this type of problem just to convince yourself it works. So what you would do is take this matrix A that we just built and confirm that if you multiply it by one of your eigenvectors, say 1, 1, 1 was one of our eigenvectors, just confirm that, yeah, that really does give you your eigenvalue times that eigenvector. And you can do the same thing for the other eigenvectors as well. So one of our eigenvectors was 1, negative 1, 0. So you can check A times that does give you double that eigenvector, so that's good. And then we had a third eigenvector, 1, 1, negative 2, and that one was actually associated with the eigenvalue 3. So you could also confirm A, 1, 1, negative 2 does give you 3 times that original vector. So I'm going to put 3 check marks here, just showing we would check those 3 facts. And if they were all confirmed, then that would tell you that for sure you had built the correct matrix A. So in this video, we've accomplished 2 things. We've found the matrix Q that orthogonally diagonalizes A, and we've also looked at the spectral decomposition to find a matrix with prescribed eigenvalues and eigenvectors. Thanks for watching.